everyone. Welcome back to the lectures and Introduction to Multi-Agent Systems. In today's lecture, we'll continue our discussions on centrality measures. After degree centrality, which we discussed in the previous lecture, in today's lecture, we'll focus on something that's known as the eigenvector centrality. Unlike the degree centrality, eigenvector centrality is a feedback-based centrality measure. So let's get started and try to understand what that is. Let us consider the network, the undirected network that is shown in this figure. This is the same example that we discussed in the previous lecture. So I'll quickly write down degree centrality of each of the nodes here. 2 is going to be 3, then 2. We can see that the centrality score is highest for the nodes 2, 3, and 5. So let's mark these nodes here, 2, 4, and 5. Again, an interesting thing that we can notice from this example is that both nodes 2, 4, and 5 have 3 neighbors. The neighbors of node number 2 are 1, 3, and 4. Out of these, 4 happens to be a central node in terms of degree centrality. Or rather, we can say 4 happens to be an important node because it has a lot of neighbors. Similarly, node number 4 has 3 neighbors again, 2, 5, and 6. And here, both 2 and 5 are important nodes in terms of degree centrality. Again, node number 5 has 3 neighbors, 3, 4, and 6, and 4 happens to be again a central node. Each one of the nodes has at least one central node as its neighbor, but node number 4 here has 2 nodes as its neighbors, which are quite central in terms of degree centrality, or in general, they're important nodes in the sense that they have a lot of neighbors or friends associated with them. Clearly, using just degree centrality, there was no way for us to distinguish the nodes 2, 4, and 5. If we just apply degree centrality, it gives the same centrality score for all these 3 nodes. To summarize it, we definitely know that really degree centrality may not be the best way to rank the nodes in a network. This leads us to something that's known as, eigenvector centrality. Let us try to understand what exactly is eigenvector centrality. We have been motivated enough that there is a need for one more centrality measure that can actually distinguish between these kind of nodes, 2, 4, and 5. Let us see if eigenvector centrality can actually do that. So let's get started. Let us consider a group let us consider a group of n individuals, n number of individuals. Were distributed over a network G with adjacency matrix A. A. Now, what happens in the case of degree centrality is that every neighbor that we have gives a point. However, note that every neighbor gives us the same point, meaning there is no way for us to distinguish between an important neighbor and a not so important neighbor. To write it formally, degree centrality each in degree or neighbor has a unit count associated with it. With it. Even if the associated neighbor has a very high centrality score or very low centrality score. So basically, it treats both of these nodes in an equal way. In order to circumvent around this problem, and in order to circumvent this issue, in the year 1987, mathematician Philip Gonisic proposed that the importance of a node should be proportional, or rather, in this measure, is proportional to the weighted sum of the importance of all its neighbors. All of its neighbors. Hence, eigenvector centrality of a node I denoted as CEVI is proportional to two aspects. First, the degree of the node I, and proximity of I, the proximity of node I to other nodes having high degrees. According to Bonasich, these are the aspects that must be taken into account, by any centrality measure when it generates a ranking. For example, for the network shown in this figure, we can clearly see that both nodes, let's highlight it, nodes 3 and 6, both of them have really high degrees, but according to the idea that Bonasich proposed, let's analyze in order to apply his theory. Let's just write out the neighbors of both 3 and 5. So 3 and 6, sorry. For node 3, the neighbors are 1, 2, and 6. And for node number 6, the neighbors are 3, 4, and 5. If you notice here, nodes 1 and 2 have very low degrees, while nodes 4 and 5 have high degrees. Meaning, by this logic, node number 6 is supposed to have a higher centrality measure in terms of eigenvector centrality. Meaning, we can write, by simply applying the logic, that CEV of 6 should be greater than CEV of node number 3. Okay, now let us define the notion of eigenvector centrality a bit more formally. A given matrix A associated with a digraph G of A. When we write of A, we simply mean that the given matrix A serves as the adjacency matrix for the digraph G. The eigenvector centrality measure, or the eigenvector centrality vector, is given by CEV. Okay, let's write it as the eigenvector centrality score. Is given by CEV of the ith node is equal to some term alpha times a summation. The summation is over J going from I to N times AJ, A of AJI and CEV of node J. So what exactly is different here as compared to the degree centrality? So what we observe here is, in degree centrality, we did not have the term CEV of J getting multiplied to the entry of the adjacency matrix. Meaning now we see that not only is this measure proportional to its degree, it is also proportional to the importance of its neighbor, which makes it different from the notion of degree centrality. This can be written in a more summarized way, this definition as in a matrix form. It can be expressed as CEV, which is an n cross 1 vector, is equal to alpha times A transpose times the CEV vector again. So what is this term alpha? Where does it come from? What should be its value? Let's try to understand why exactly, first of all, it is known as the eigenvector centrality. And once we understand that, then we can easily calculate what the value of alpha should be. Let's see. So just rewriting this slightly. So this implies that, okay, let's take a transpose on both sides. Then what we have is CEV transpose is equal to alpha CEV transpose again times A. This further implies that CEV transpose A is equal to 1 by alpha times CEV transpose. Let us observe this expression. If you look at it closely, you'll realize this is nothing but the expression of how we calculate, or the expression of an eigenvector and eigenvalue, basically an eigenpair of a given matrix A, where 1 by alpha is the eigenvalue associated with the left eigenvector CEV transpose. Meaning in this expression, CV is the left eigenvector and one by alpha is the associated eigenvalue. Okay, so what should be the value of this? So which eigenvalue should we choose? Based on that, we can figure out what the value of alpha should be. In order to understand that, let's quickly remind ourselves of what we already know about non-negative matrices. We know that in the case of any non-negative matrix, using the Perron-Frobenius theorem, there always exists a dominant eigenvalue. So what is the role of this dominant eigenvalue and the associated dominant eigenvector? The answer is that whenever we are trying to calculate the solution of any dynamical process, which evolves using, let's say, the distributed averaging model, for example, the system dynamics generally converges to the dominant left eigenvector of the matrix. Hence, ultimately, what eventually remains in the solution is the left eigenvector. Hence, it makes sense that we consider the left eigenvector while calculating the centrality of each node, meaning 1 by alpha should be equal to the dominant eigenvalue. So let us write this here. Since the system dynamics, of a system are, we cannot say always, so we'll write are generally governed by or, okay, let's rephrase this slightly. Rather than saying the dynamics are governed by, we can say the trajectory of a system is generally along the dominant left eigenvector. Associated with the dominant eigenvalue, let's say dominant eigenvalue, say lambda p. Lambda p, the subscript p here arises from Perron itself. Okay, meaning the 1 by alpha that we have here must be equal to lambda p, meaning alpha is equal to 1 by lambda p. Now, lambda p is nothing but the spectral radius in the case of non-negative matrices. So we write here that alpha is equal to 1 by rho of A, which is the spectral radius. Let's go back to this example that we have already seen several times. Let's try to calculate what should be the eigenvector centrality. So please pause the video here, calculate what is the dominant eigenvalue, and associated to that, what is the corresponding dominant left eigenvector, and that gives us our centrality scores. So what I'll do is I'll directly write the solution here. CEV here is a 6 cross 1 vector given by 5.21.17. Which score is the highest here? That is the score associated with node number 4. Notice that this is in line with the definition of eigenvector centrality. Why? Because 4 is actually associated with 2 very important nodes in the network, unlike 2 and 5. That's why it is in fact justified that 4 should be eigenvector centrality wise the most central node in the network. Let's apply the notion of eigenvector centrality now to a directed graph. Let us consider the directed graph shown in this figure. So I'll again ask the students to pause the video right here and try it first by yourself and try to calculate what should be the eigenvector centrality score. In the interest of time, let me directly write the solution. The solution that we'll get here is simply a vector of all zeros. Meaning, what generally happens is that in the case of acyclic networks, eigenvector centrality generally does not reveal any meaningful information. Let us write this observation. Eigenvector centrality performs well for generally strongly connected networks, strongly connected digraphs. Of course, it works already for undirected graphs that we already know, but there are some issues that we face in the case of digraphs. Note that it also works when the network has a set of globally reachable nodes which are strongly connected and aperiodic. However, it fails to convey any meaningful information in the case of acyclic networks. Which is a major flaw because there are several real world networks which are actually directed in nature. Just to give an example, let us consider citation networks. So in the case of citation networks, we know that there could be some papers, a few papers, which are very highly cited. Let's say this node here represents a paper which is cited several times. However, it's not mandatory that the paper that's given here goes back and cites each of these papers, meaning citation networks are mostly acyclic, meaning we will not be able to apply the eigenvector centrality measure to get any meaningful information. What does this mean? This means that we now need yet another measure of centrality, which can now be applicable to a wider class of networks. That brings us to the notion of Kac centrality. So it's something that we'll discuss in the next lecture. Thank you.